welcome everyone. Just to give you a little bit of background, this is the Distinguished Speaker Series, which is part of the National Science Foundation sponsored IGERT program that we have here at WSU, which is designed to recruit PhD students into the general area of smart environments. And of course, part of that program is to fund speakers to come in and tell us about work that's going on outside of WSU. So today we have Dr. Shwetak Patel from the University of Washington, Computer Science Department. And he is going to talk about work on energy monitoring and low power sensors.
Thank you. It looks like the picture you have on there is the same shirt I have on now, so it's a little bit embarrassing. But thanks for the introduction, Larry. So my name is Shwetak Patel. I'm from the University of Washington. I actually also have an appointment in Double E. So I'm in computer science and engineering and electrical engineering, with my home department being in computer science. So today I want to talk about some of the work that my lab's been doing in residential energy monitoring technology, and also looking at some new ways of doing low power wireless sensing in the home. Before I get into that, I want to give you an overview of the kind of work that we do. So we work in the area of ubiquitous computing, which is the idea of moving away from the normal desktop metaphor that we've been accustomed to, and looking at interaction in the general environment itself, and looking at ways that we can build sensors and embedded systems to support that vision of ubiquitous computing. We also do a lot of work in human-computer interaction, looking at ways that these applications can actually drive these actual usability and adoption of these technologies, and also ways that we can build new user interface technologies as well. So the lab that I run at UW is fairly broad, and we cover a lot of these different aspects of computing. But the focus of this talk in particular is on sensing in the home. In particular, looking at sensing technologies for electricity and water monitoring. So we've been doing electricity and water and gas monitoring, but I'll focus primarily on ways of monitoring energy and water in the home environment. And then I want to switch gears a little bit and talk about our low power wireless sensing applications that we've been working on, in particular a new platform for doing low power wireless sensing in the home environment. Okay? So the overall goal for our work in the energy monitoring space is essentially help consumers reduce their residential consumption. Right? The way that we're trying to do this is looking at ways that we can provide granular information to consumers about where their energy is being consumed. So granular meaning itemized feedback about exactly what devices or appliances are consuming how much energy. And so if you have access to that information, you can encourage consumers to reduce their consumption in the home. So you might think about, why are we focused on the residential side, right? Isn't most of the consumption actually the large businesses that are out there, large industry, or the big power plant that's down the road? Well, it turns out that the residential consumption in the US makes up for about a quarter of our energy expenditure in the energy side. All right? So this is still a significant portion. This is our day-to-day activities impacting our energy consumption. More interestingly, on the water side, more than half of our water consumption comes from the residential use. All right? So one caveat here is this is treated water, not water just for irrigation or for crop use. All right? This is treated water. So irrigation is actually a substantial portion. But for treated water, more than half is actually residential, and commercial is a very small piece of that pie. Although a lot of work has focused on energy, I think water is actually going to be this next big area that we're going to have to start to focus on, because that's not a renewable resource. In fact, a lot of the states in the South or even the Southwest are struggling with water concerns where they only have about 100 days of water left at any given summer. All right? So water is also a really interesting focus for looking at ways that we can reduce consumption in that space. So what's the user experience on water or electricity or gas feedback for the normal consumer? All right? So it's akin to a grocery shopping experience that's like this, where let's say you go to Safeway, where you have this aisles of different products you want to purchase. They're all well labeled, and at the end of the grocery shopping experience, you get this nice receipt. And it turns out Safeway does a good job of kind of categorizing your receipt now. So you can get a category on grocery, refrigerated goods, general merchandise, baked goods. So you kind of know where you're spending your money, but also at category levels as well. But you can always look at the receipt to see, where did I spend so much money after this Safeway experience? But what if I told you that Safeway was going to change to this new model where they gave you two pieces of information: how many food units you purchased and how much you owed at the end of that experience, right? Well, you'd probably complain that you don't have that kind of feedback, all right? And your electric bill, for example, is actually not like that. It's actually like this latter half, which is basically you get two numbers, which is kilowatt hours, which is some nebulous term that a lot of people don't know what that is, and how much money you owe at the end of the month, right? But you don't get this itemized breakdown. Why is it that we get a credit card bill that's broken down into different purchases, and even our telephone bill tells us exactly where each call was made, but our electrical water bills are actually something where we're used to just getting one piece of information that's not even actionable, all right? And so that's one of the challenges that we're trying to address, is how do we provide actionable feedback? But just to get to that point, we've got to have a way to itemize and decompose consumption in the home, all right? So here's an example of a Seattle City or Seattle Public Utility water bill. So you have some information here where it gives you a little trending chart, all right? So how much water you consumed the previous month or the last 12 months. But look at this little anomaly, right? There's this huge jump, right? But you don't know what happened to get this big jump here, all right? And so a lot of these numbers are pretty nebulous as well, or really esoteric, CCF, GPM. What does that really mean in terms of what I'm consuming? So incidentally, look at this water bill. This is a $3,000 water bill that one of my colleagues at UW unfortunately received last summer. And so what happened was his irrigation system actually ended up leaking outside, didn't notice it for 2 billing cycles. In Seattle, we get a bill every 2 months. All right? So it took 60 days before he saw a bill that said that he owes $3,000 and he had consumed 100,000 gallons in that 2-month period. All right? And so what they sent him was this very large bill with a little dye pack in there that says, put this in your toilet to see if you have a toilet leak, right? But it turns out the toilet couldn't even consume that 100,000 gallons, right? So even the utility has no idea where the consumption's happening, right? All right. So now we're looking at ways that how can you build a bill that actually has an itemization aspect to it, where you know where the things that you're consuming are coming from. And also, in addition to that, build user feedback interfaces where you can start to present this information in a very different way, having in-home displays and having actionable feedback about, what could you really do to reduce your consumption. So these are just some examples for the electricity and water side where you can start to give you a breakdown of, how much is the bedroom TV consuming versus the bedroom itself versus other parts of the house. So you can actually know where to tailor some of your conservation activities. And it turns out that work in conservation actually stems back to the late 70s, where environmental psychologists found that if you gave somebody disaggregated feedback, which is feedback based on itemized consumption, you would actually see a reduction in 15 to 20% in overall consumption sustained over many years. So just by giving somebody that feedback, you can already reduce consumption by that amount. Right? So there's already some hope here that we can reduce residential consumption if we have access to the data. But the problem is how do you actually get the access to that kind of data? Where going into the home, you're not going to be able to figure out exactly what things are happening from just a standard meter. And so there's a lot of values from a variety of different stakeholders. The consumer can look at new conservation activities and have feedback on what they can do. But also the utilities and scientists can actually benefit from this end-use information, because right now the models on end use, so end-user appliance use, is actually not very well known. In fact, a lot of it is self-report. You ask somebody how much they consumed and where they consumed it, they're going to under-report it or be grossly inaccurate. And so there's there's reason why you want to actually have this corpus or this data set. And also, if we have a better understanding of people's consumptions, we can validate and verify if some of these new conservation activities that the federal government and utilities are actually mandating, are they actually effective? But there's no way to actually evaluate that right now. So the technology you have right now is this thing that's outside your home, right? This ugly box-looking thing that basically has no purpose for the end consumer at all, right? This is something for billing purposes only that the utility uses to figure out how much energy you consumed. You might be able to read the numbers and make some sense out of it, but it's not giving you real-time information that's really useful or actionable. And so what would you have to do to get information down to each appliance? Well, one thing you could do is build a distributed sensing system where you maybe build a wireless sensor that goes behind each one of your appliances. We put one behind the microwave, coffee maker, bean grinder, refrigerator, and then all the lights, right? Well, this is not going to scale in a home environment where it's going to be really difficult and time-consuming to install a sensor device behind every appliance, all right? And so one of the things that we've been looking at is, are there other ways that we can get that information with minimal instrumentation to the home? And so some of the work that we've been doing is called infrastructure-mediated sensing, which is the idea of using the utility infrastructure as a sensor itself. So the utility infrastructure, like the water and the electrical system, already permeates throughout the entire home. It already touches all the periphery of the house. So can we use this physical infrastructure as a sensor? Kind of like snooping a wireless network or a Ethernet network to figure out the activities that are going on in that particular setting. But here, can we snoop the power line or the water infrastructure to figure out, well, what appliances are being used without having a distributed sensor network? So that's what we've been doing in the last couple of years, is using the utility infrastructure to give us that information about energy use down to each appliance. And so one way we've been doing it in the electricity side is a single plug-in sensor that plugs into any arbitrary electrical outlet that monitors the line voltage to figure out what devices are being turned on and off. Okay? So how does this work? Well, so the existing approach, the way that people used to solve this was, well, they would get the data from the meter somehow, and they would look at the change in power consumption in real time to estimate what's being turned on and off. So if the oven turns on something that consumed maybe 1,000 watts, that could be your oven. If something that consumed 100 watts, that might be a light bulb. But there are a lot of things that are 100 watts. Your DVR, DVD player, some TVs are 100 watts. So you won't be able to tease that apart. So just look at the power isn't enough. So what we've been looking at is something that's a little different. We're actually looking at the electromagnetic noise that's emanated over the power line as a result of the use of these devices as our signal to figure out what devices are happening. So this accidental noise is our signal now. So this EMI noise propagates as a result of the variety of different switching devices on the power line, be it a switch that's just a light switch that's connected to an incandescent light bulb, or the power supply in a laptop or a CFL or a compact fluorescent light bulb. But using this noise to kind of reverse engineer exactly what devices are on and off in your house, right? And so this is already there. This is existing infrastructure that you don't have to deploy. The only thing you deploy is this one single plug-in module that's monitoring the power line infrastructure. So here's one example of where this noise comes from. Let's look at switch mode power supplies. So SMPSs are very popular now. So SMPS is basically a way to take down 120 volts down to a reasonable maybe 10, 12 volts DC so you can run your consumer electronic devices. This is more efficient than a traditional linear power supply because you're not dissipating the extra energy as heat. Here you're actually switching it on and off quickly so that you're actually reducing your overall power consumption. SMPSs are pretty much mandated in a lot of parts of the country. In fact, Energy Star requires SMPSs for most consumer electronic devices because they're more efficient, smaller, but as a side effect, they produce continuous noise because of the switching mechanism that's in there. So the switch mode power supply's internal oscillator happens to be switching at a particular frequency, maybe 150 kilohertz, that we see over the power line. And by looking at that signal, we can actually try to figure out what that is over the power line. So what kind of things do you have SMPSs in? Well, light bulbs, CFL light bulbs, LED, LCD TVs, iPhone adapters, laptops, PlayStations, gaming consoles, pretty much any consumer electronic device these days has an SMPS. So you're going to see more and more of these. And so you have a great opportunity to get a lot of information about the different devices in your home, even some of the smaller things that were harder to get with the previous approaches. So let's look at, for example, a spectrogram on your power line. So if you had a spectrogram of your electrical power line infrastructure, what would it look like? So this is the frequency domain. So this is a waterfall plot where time is going up. So this spectrogram is going up, so time is going down. And these are all the switch mode power supplies that are over the power line, right? So you have things like the CFL bulb, the washing machine's microcontroller inside of it. Modern washing machines actually have a switch mode power supply because they have a micro that turns on and off the cycles, all right? This is the TV turning on and off. These are all the internal oscillators for the SMPSs. And one of the things that's interesting to note is they're all over the place, all right? And also, the waveforms are different. So I'll talk about that in a second on how we take advantage of that. But let's zoom in a bit. So here's the lamp. This is the compact fluorescent light bulb, where it has a pretty tight frequency. Actually, here's the harmonic of it. This is the fundamental, and that's the harmonic, where it's basically switching at one frequency. It doesn't need to do much, right? It's just switching at one frequency, and then the amplitude is modulated based on the temperature of the room because the bulb needs to heat up and cool down. Whereas, let's go back for a second and look at the TV. The TV is a bit broader. What it's doing is sweeping. As the backlight of the TV is modulating, it actually changes its center frequency because it's compensating for the amount of power you need to put into the TV. So now you can look at the signature to figure out, well, what kind of device was it? Well, if it's this modulating thing that's centered around a few hundred hertz, then that's probably a TV. Whereas a CFL is going to be drifting with temperature and be a little bit more stable. Whereas a PC is going to have a different signature. So using the EMI signature, we can figure out what kind of device it was. And the nice thing here is that each of the devices are resonant on different parts of the spectrum. If you took two light bulbs that were from the same manufacturer and same brand, and you turned them on simultaneously, what you would see is they would be roughly in the same area, but they would be apart by a few hertz. Because of the internal construction is about plus or minus 5 or 10% for all the different components in there, will give you enough variance to actually count the number of devices you have, even if they're the same ones. So even if you had 2 or 3 TVs in the house that were the same brand, you can still tease those apart. So what does the sensor interface look like? So I won't go into a lot of detail here. You can take a look at our website to get the low-level details. But our sensor actually plugs into any electrical outlet. So on the front end, the hardware is actually a power line interface module. Essentially, it's a high-pass filter. We have to actually get rid of the 60 hertz cycle because that overwhelms basically our digitizer. So it's a high-pass filter that's impedance matched to the power line. And then we have a digitizer that basically does FFTs in real time. So we have a DSP that's constantly computing a FFT on this waveform. And then we have a machine learning pipeline that does the event processing and machine learning off of it. So the event processing actually has 3 steps. First, we do event detection and segmentation, finding that a particular appliance is turned on and off and segmenting it out of all the background noise. Then extracting the relevant features and then running our classification algorithms to figure out, well, what was it? So I'll quickly go through that step by step. So if you look at the power line, there's a lot of noise that's in the background. So I mean, there's going to be a lot of signals of interest, but at the same time, there'll be other things there as well. So what the DSP does is it constantly computes the background noise. So we take a snapshot, and we constantly keep taking a snapshot until we see a change. All right? So let's say a light bulb, a CFL light bulb turns on. You actually see a change in the EMI baseline, and we just take a difference vector there to say, well, you know, our baseline noise changed past some threshold. We're going to take a difference vector, and that's our signature for this thing. So this is basically a difference between the noise floor and the EMI of this light bulb. So this is how we segment a particular event occurring. And so now we extract the different features from it. So we look at the center frequency, where it occurs, because it turns out, depending on what brand it is, it's going to be different in the spectrogram, because a GE bulb can't interfere with the Sylvania's patents on how they do switching for a switch mode power supply. So they happen to be different. All right? The bandwidth of the signal, so what is it really doing? CFL versus the TV is a good example. The amplitude of the signal, and then the frequency shift. So the temporal nature of this signal. So looking at all of these features to characterize what appliance it was. All right? And then classifying this using 2 different schemes. We use nearest neighbor and a support vector machine algorithms, where the nearest neighbor tries to figure out the closest set that we have in our database, and using support vector machines to actually do some more of the fine-grained temporal and time series aspects of the classification. And so the way you can train this is there's 2 ways. One is you can actually train it manually in your home, saying this is my TV and this is my light switch, and then it's calibrated that way. The other way that we're training the system is we're actually creating models, generic models of how these devices look, so that you can actually do this in a semi-supervised way, where look, here's what TVs look like. We don't know that it's the one in the bedroom or the living room, but we know it's a television, and you have 2 of them. And there's a couple ways to get that information. One is you can crowdsource that, right? So if somebody were to label their device, because this is an algorithm that's running in the cloud, you can actually take advantage of that. Secondly, you can actually look at the FCC specs for all these appliances. They all have to conform to certain FCC regulations, and they all have a spectrogram of their EMI noise. So you can actually scrub all the FCC data sheets to get this database without even having to touch an appliance. All right, so there's many ways to get that information. So we can train general models or instances of it, and we've been working on both. So in one evaluation where we took 7 homes where we instrumented every single fixture, every appliance for ground truth data. So we needed to know when the TV turned on, when the light turned on. We did this in 7 homes. It took days and days to instrument every home, but we had to get the ground truth information. And so what we did was we had our device in parallel with the ground truth system to see how accurately it would actually identify the different appliances. So there were roughly about 50 devices in each home, appliances and consumer electronic devices. So a significant number. And so the average accuracy was about 92% in identifying not just the category, but exactly which device it was. Was it the upstairs TV versus the downstairs TV? Was it the iPhone charger versus the iPad charger? So we were actually pretty aggressive in what we were trying to identify here. So everything was above 90%. There were a few homes that were actually lower in the mid 80%. Those 2 homes were interesting in that a lot of the confusion was actually not confusing a completely different category of devices. It was actually confusing similar models. So for example, we had this Samsung LED TV, 2 of them. It was actually confusing those 2. even though we can separate those out, every now and then they actually confuse each other. So if we lump those together and categorize them, then the accuracies would be much higher. All right, so if you look at the confusion matrix, the confusions were actually making sense there. Here's just a list of the kind of detectable events. And I don't want to go into a lot of detail here, but I just want to point out a few things. Some subtle things like microwave, refrigerator door, and electric oven door. So you might think, how do you get that information, right? Well, it turns out that those things are tied to a relay, which is tied to a little light. When you open your fridge, lights turn on, right? And so you can get the light inside your fridge to know when some of these events are happening. So there's other implications with activity sensing that you could do that have some more implications for elder care and activity monitoring in the home, where you can tie together a lot of these different events to figure out people's activities and patterns. So I talked about event detection, when things are turning on and off in the home. But what about power consumption? How do I get power consumption? How do I know that the TV consumed 100 watts? Well, one way to do it is to correlate with a smart meter, right? But the smart meter is not going to give you real-time information all the time, right? So we had to build a different consumption sensor that was also easy to deploy. So a traditional way of doing that is you'd go inside your breaker panel and add some current transformers or CTs in them, right? Obviously, a normal homeowner wouldn't be able to do that. In fact, electrical engineers can't do that. You have to be a certified electrician to do this. And so how do you get power consumption information that's end-user deployable? So what we did was we built a device called the contactless current sensor. So this is a little sensor that goes onto the outside of the breaker panel. And it infers the whole house power consumption based on inferring it from the power going through the bus bars in the electrical panel itself. So where these breakers connect to, there's two zero-gauge wires that are going down. And so this is actually inferring the current consumption through the metal. So literally, the user experience here is you take the little sensor, which is wireless, you peel off the back tape, and you line it up with two of the breakers, and then it basically is inferring how much power is being consumed by the whole home without even touching the wire. So this actually telemeters data to the plug-in module to tell you how much power is being consumed at that instant. So we're within about 4% of true power there. So it's actually pretty accurate for doing the kind of disaggregation that we're trying to do. But just by itself, you can use this as a smart meter if you wanted to, if you didn't have access to one in your home. All right, so I'm going to change to water sensing now. So is there a similar analogy in the water side? Can you build a single point, easy to deploy sensor that gives you information about exactly what water fixtures are being used? And that's what we were trying to do with the HydroSense technology, is try to figure out how much water each device is consuming without cutting into the pipe. In the water space, it's even more challenging, where the retrofit is you have to cut in line with a pipe and actually install it. So this is even harder to install, right? And water meters actually don't give you this information at all. They're typically buried down the street, even if you can find it. And so traditional inline water meters aren't really easy to install. So we're looking for an easy to deploy way of figuring out exactly what water fixtures are being used in a home. So a quick plumbing primer. So if you look at how the plumbing infrastructure is laid out in a home, is you have water coming in from the municipality, and then you have it essentially branched out to a variety of different fixtures. A couple of things to note. Hot and cold are actually tied together. They're tied together through a water heater. You can think of this as a large capacitor in a sense. Okay? So that'll make sense in a little bit, but they're technically tied together. And everything else is also tied together too, because it's one pipe going in that's branching out. And so the place that we installed our sensor is actually a pressure sensor at a hose bib. You know how to put a hose on a hose spigot, so you can screw a sensor on there. And so that's what we do. We screw a hose on the hose bib. We screw a little pressure sensor there. And what it monitors is actually the water pressure fluctuations of the uses of all of these different appliances. So there's a complete analogy here in the electrical side, which is EMI noise. There's actually pressure noise that's generated from the use of these different fixtures. And because they're all interconnected, you just need one of them. So no matter where I flush a toilet, you're still going to see it from this one sensor point. And you don't have to cut into the pipe, and it's a place where an end user can install their device. So here's what the waveforms look like. A faucet, toilet, and tub. Depending on the construction of the valving and the type of fixture it is, the waveforms actually look different. So this is called water hammer. Basically, when you open and close the valve, the change in pressure will cause this impulse response. So a faucet, toilet, and tub look different because the valving is different for each one of those things. And if you have two toilets in the same house, well, they also look different. Even though the shape looks similar, the characteristics of the shape are going to be different because where they lie on the plumbing infrastructure. Because the plumbing infrastructure, again, is a transfer function from the originating source to the sensing source. So even though the shape is the same, the characteristics will be different. And so that's what we do. We categorize what kind of fixture it was, and then use the nuances in the signal waveform to figure out, well, was it toilet A versus toilet B? So here's an actual bathroom sink. This is real data from a home. So this isn't just a simulation. And you can tell how clean this is, right? I mean, if you had signal data like this all the time, you'd be happy. And so this is the open event and the close event. So you have this impulse response, so basically the pressure going down when you open the valve, and when you close it, you get a spike going up when you close it, because you basically have all this kinetic energy, you close the valve, and you have this reverberating water system basically in your home, right? And so that's the end event there. And so the shape of this waveform tells you what kind of fixture it is, but these little subtle changes in pressure tells you how far along the plumbing infrastructure it resides. And so the way it works is we first try to detect if a water event even occurs, classify the event as an open and close, determine where it comes from, and then estimate the flow consumption. So I'll go through a quick example. So let's say we have a raw pressure signal. That's what we get from our sensor. The first thing we do is we smooth it using a low-pass filter, and then we compute the derivative of it. So it's hard to see because it's red, but basically we're computing the derivative, the rate of change. So we use these three different process views to do the feature extraction. So the first thing we look at is, as the pressure is changing, we look at where the first critical change in pressure happens. Okay, so when the derivative drops down. And then we look at when the pressure stabilizes. So this is, let's say you flush the toilet. All right, and then we figure out, okay, we know where it stabilized. We know how to segment this now. The event happened here. It stabilized here. Here's the signature for that particular toilet flush, for example. Right? And then what we can do is go to this other process view and say, what was the pressure change? The pressure change can help us figure out how much water was consumed. And then we can look at the derivative and say, was it positive or negative? If it's negative, it was an open event. All right? So now you can say it's an open event. We know how much water was consumed, and we have a signature to identify exactly what fixture it was. And so we use match filtering to figure out what fixture it is. So we've created a database of models on what commonly occurring fixtures look like. So here's a model for a toilet, faucet, and a shower. And so we use that waveform to pattern match which one of these are. And so it's dependent on the fixture type, valve, and location of where they are in the home. And so evaluating this is rather challenging. So some of the things that we did initially was staged evaluations, where we would flush a toilet, mark it on an interface to say exactly when it happened for ground truth. We'd go in and turn off a shower, turn it on, turn it off, do that repeatedly, and mark it on an interface. Right? But it's not very naturalistic. We were able to get great results here to validate the feasibility of it, but we want to know how many times do you have compound events? How many times do you flush the toilet and wash your hands? How many times do you have your dishwasher running and you're washing your hands in your sink? Looking at more naturalistic data is probably more realistic in terms of what you might see in the waveforms. So what we did was we took a number of homes and instrumented every single water fixture in the home for figuring out exactly what water was being consumed, is hot, cold, what mixture, and which one it was consuming. So we basically had data loggers, wireless data loggers that were instrumented throughout an entire home. So we knew exactly when these things were occurring. So now we could correlate that to our sensor stream. So we had 15,000 events in one of the recent deployments of 5 homes that we did. So in isolation, we're about 97% accurate. We know exactly what toilet's being flushed with 97% accuracy if that's the only thing that happened. But when you flush your toilet, likely, hopefully, you will wash your hands. And so when you start washing your hands, you're in a compound event. Right? The toilet's flushed, it's filling up, and you're washing your hands. So you're in what's called a compound event. So the waveforms look a little different from their isolated views. So when you're in a compound event, it's about 90% accurate, which is still pretty good. And what we found is the number of compound events in an actual setting is about 27% of the time. You would think there'd be a lot more double compound events, but only 27% of the time there's compound events. And a lot of the confusions were among similar fixtures. Confusing the one toilet from the other, kind of like in the electrical space. But yeah, even in the naturalistic case, we can still get high 80% accuracy in identifying the different events. So I've talked to you about 2 different approaches on doing easy to deploy sensing for the residential space, where we're getting information about each different appliance and fixture. Now you can feed this information back to consumers through bills that have itemized feedback or through user interfaces. But the other thing that we're starting to work on, so switching gears now to the other part of the talk, is, well, how do we generalize this? So one of the things we want to do is, well, monitoring the plumbing and the electrical will give you some information. but it's not going to tell you what the temperature is in a building. It might not tell you if you have some other issues going on. You can't use it as a motion sensor, for example. So what are some ways to do easy to deploy, low power, general purpose sensing in the home? Let's say I want to add any sensor capability to a home. Is there a way that we can do that that's low power that can be long lived? So that's the other part of our research that we've been doing. You can put a lead, humidity, mold sensor, or whatever on this, but you do it in a low power way so that they're actually going to be practical. So that's what we've been working on now, is new approaches for low power sensing. The idea behind this is in a smart home environment, you're eventually going to have sensors everywhere. They're all going to be wireless. We know how to do wireless really well these days. And that's going to be pretty easy to set up. But the challenge is they're going to be hard to maintain, right? Because how are you going to replace all those batteries? So that's a huge challenge right now. And a lot of folks have been looking at wireless power transfer, other ways of trying to power these devices. But those are actually only limited to certain kinds of phenomena. So are there ways that we can build the sensor nodes in such a way that they're so low power that you still use batteries, but they're so low power you don't have to worry about replacing them for 20, 30, 40, 50 years? So that's what we've been working on. So our sensor platform is called Snoopy, Sensor Nodes Utilizing Power Line Infrastructure. So this is a general purpose sensor platform that is very low power. And I'll show you how low power in a second. So what makes Snoopy novel? Right? There are tons of sensor network nodes out there. This is yet another one I'm standing in front of you talking about. Right? You can go off the shelf and buy tons of these, Zigbee, Wi-Fi, Bluetooth, anything you can think of. So why yet another sensor node? So let's just do a quick comparison between the existing sensor nodes that you can buy off the shelf and the one that we've been developing, Snoopy, just to give you a comparison. So let's look at peak power consumption, how much power it consumes in transmitting data wirelessly in an environment. And so we're going to look at this from three different aspects: the communication, the amount of power that the radio consumes in terms of transmitting it, computation, so the CPU, and then the total power. All right? So if I plot both of these here, Snoopy is actually so low power you can't even see it on a linear scale. All right? So I'm going to zoom into this and use a log scale. All right? So this is in log scale. So existing sensor network nodes, if you look at just the radio, the power for transmitting data wirelessly, the radio communication, it's usually orders of magnitude higher power. So basically, here you're nearly 100 milliwatts of power consumption to transmit data within a home. Whereas Snoopy is lower than the computation itself. So Snoopy is actually a magnitude lower than the power required to actually do the computation on it. So what that means is if you look at the computation and communication the communication-computation relationship, they're reversed. Typically, you spend a lot of power transmitting the data away than computing it, whereas in the Snoopy case, you actually spend very little power transmitting the data. All right? Well, the other thing that's important is the power output for these two nodes is the Snoopy is 2 orders of magnitude lower in power consumption for the transmit power itself. These are both set up to go whole home range. There's no repeater or anything installed at all. These are set up to give you the same range and the same throughput for both. But it's still orders of magnitude lower power. And if you use the same computational system as what these folks used on this side, the total power is still 1 order of magnitude lower. Okay? So in essence, if you look at this, the Snoopy node consumes about 65 microwatts of power to do wireless sensing. So how does it do that? So how do we do 65 microwatts of wireless power sensing with still whole home range? So the way that we do this is that we utilize the power line infrastructure in a different way. And we also have some highly optimized custom hardware that we've built for it. But more importantly, it's the utilization of the power line infrastructure that enables this. So what we do is we use this concept of what we call power line coupling. So what power line coupling is, it's the idea that our receiver is plugged into an electrical outlet, and we're actually using the power line, the physical copper in a building, as a receiving antenna. Instead of having a separate dipole antenna that's inside the receiver, the entire wiring in a building or a home is actually the receiver. All that copper that's there is now the receiver. So the sensor node, as long as it's near the power lines, it can transmit the data by coupling over the power line, and the power line is actually a large antenna. And so what that enables us to do is to turn down the power so low power that you can consume less than 100 microwatts of power and still get data around anywhere in the home. And so this power line coupling idea is how we're able to get low power consumption out of these things. So let's look at an example scenario here. So let's say we take a home and we have a base station let's take traditional wireless communication, Zigbee, Bluetooth, Wi-Fi, whatever you want there. And notice that there's two antennas that are sticking up there in the middle of, let's say we place it in the middle of the home here. And our sensor node is in the lower left-hand corner. So when you want to get data from that location to the wireless base station, you have to transmit at a high enough energy so that you can actually get past all the walls and get to the base station, right? With power line coupling, you still have one base station. It doesn't have the antenna. It's plugged into the wall, and so it uses all the copper in the walls, where it's red, as the antenna now. You take that same node, it only actually needs to transmit at a rate that's just a little bit higher than basically a few microwatts. So it just needs to go to the closest power line. You don't actually have to transmit all the way over the air. So let's say you move the node to a bigger room. Well, you got to transmit at a little higher energy, but still, it's still less than what you would do to go all the way over the air. So in fact, what this implies is, with the Snoopy approach, as you have more walls and the house gets bigger, the better it works. Whereas traditional Wi-Fi, as you have more walls and bigger space, it actually degrades in performance. So there's a change in the relationship there as well. It actually works better as you have more walls. So this is strongly frequency dependent. You can't just use the power line for antenna for Wi-Fi, for example. So it turns out that the ISM band 27 megahertz is the perfect, the power line is a perfect receiver at 27 megahertz. So our receiver, the thing that's plugged into the wall, and our transmitter is actually tuned for 27 megahertz. And that's what we're using. We're actually using the ISM 27 megahertz band as our frequency carrier. So orders of lower magnitude in terms of just the frequency output. So it's not 2.4 gigahertz or 900 megahertz. It's actually much lower than that. So the hardware is basically a general purpose node. It's 3 centimeters by 3 centimeters on a side. It runs off of a little coin cell battery, a CR2032, something that you can easily get at a drugstore. It's fully programmable. It gives you whole home long battery life. Off the 60 to 75 microwatt consumption, a little coin cell battery with some simple sensors will last about 20 to 50 years. It's so low power that the battery will start to corrode before it runs out of energy. So now you can start to imagine long-lived sensors in a home where you can start to deploy these once and don't have to worry about replacing the batteries. And so right now, it's a low throughput application. So the current sensor node that we have is a 10 kilobit per second node. The second generation one that we're working on is roughly about 100 kilobits per second. So very similar to Zigbee and Bluetooth. So you can actually start to do video and audio over it. So here's a block diagram of the sensor platform. So we're using a MSP430 microcontroller just for a micro. The next version will have a custom micro that we'll build. It uses a custom FSK transmitter that we've built to get it to this low power. And like I said, there's a bunch of different sensor inputs that you can put your custom sensors into. And then there's a programming interface so you can write whatever code you want in C for it. So it is general purpose. So you can plop this into any home or business environment. So let me show you some range tests, so how far it works. So this is an example in a 280 square meter home, so 2-story home. The lower and upper floor, the red indicates where our base station's plugged in, so we just arbitrarily plugged into the middle of the house, or on the first floor. And the blue dots indicate where we took sample readings. So we moved the sensor node in these different locations and took the signal-noise ratio data. Took the SNR values at all those locations to get a sense of, well, how far does this really extend and how well does it work throughout the entire home? Right? Are there going to be spots where you don't get good signal? And so in the range test, this is what it looks like. So everything that's red is above 15 dB SNR, so well above 15, probably near 30, 40 dB. So any modulation scheme would be able to handle that. So we're just going to ignore all the red ones because we had signal-noise ratio that was well above what we would need for any error code correction scheme or modulation scheme. But the more interesting ones are the ones that are in kind of blue and then the yellow, the ones where the SNR was starting to be below 15 dB. So some of the places that we saw that was kind of in the middle of a room where the proximity to the power lines make a difference. Well, that makes sense. Our Snoopy node was set at 65 microwatts. It wasn't modulating the power output. So we said, at 65 microwatts, what can we do with it? So when you get to the middle of the room, you start to get lower SNR because you're getting further away from it. We could turn the power up just a bit to cover this entire house, but this was just going to just show where the challenges might be. We could still theoretically transmit data here, but it's still going to be lower than the other areas. So proximity of power lines definitely makes a difference. The corners of the rooms were interesting. Here it turned out that there were no electrical outlets there. So the electrical outlets tended to be on the other side of the room, so there were actually very little wiring here. Whereas the corners of other rooms worked fairly well because there were power outlets there. And upstairs, there's lighting from the ground floor that was going in the ceilings as well. So these centers had no issues because you had lighting, ceiling lighting from up here that was affecting it. So you actually get access to that as well. So it's only in places where you don't have a lot of electrical nearby. The other thing that's interesting is the power lines can be extended. So what this means is we had a corner of a room where we weren't getting a lot of good signal. So what we did was we got an extension cord, plugged it into an electrical outlet on the top right-hand corner of the room, and just draped it to the other side of the house. We didn't even power it up. We just draped it. And it increased this SNR by 10 dB. It was basically red at that point. So you can imagine just moving a lamp will increase your signal strength, right? Because remember, this is part of the electrical infrastructure, and in essence, is also your antenna. So this is kind of a different way of thinking about how you would extend your your wireless range, right? You take your Wi-Fi router, you move it around your house. Here, you just move your lamp around, and now you have a better signal there. But the other thing that was interesting is that plumbing helps too. These square boxes here were bathtubs. We put the sensor node in the middle of the bathtub, and it had no power near there at all. But what was happening was, in most homes, if you have copper plumbing, it's grounded to your electrical infrastructure, right? You're required to ground it. And so you can actually use the copper plumbing as an antenna too. So we're kind of getting this extra benefit from the copper in the plumbing too. So what are some of the use cases? Well, one of the things we've been looking at is long-lived sensor deployments. If you have a sensor node that can last 20 to 50 years on a single battery, you can start to install these things in an attic, crawl space, behind walls. Start to do all this monitoring in a home where you don't have to go back and replace those batteries, because how often do you want to go through the crawl space to find these sensors? You can throw them in there after they run out of a battery in 20 years, throw some other sensors down there, or just try to find them again. Right? So long-lived sensors for hard-to-reach areas is where we're trying to look at some applications in this space. So we're working with a number of folks that are interested in doing, for example, in-home health monitoring, the health of the home itself. So insurance companies are interested in monitoring different aspects of the home to see if there's potential issues that are about to arise. Methane, mold infiltration, humidity changes, potential leak problems. And knowing this beforehand, before a problem occurs well beforehand, it's highly motivating for them. All right? But the problem is, how do you even get a sensor network deployed in a house? Right? A consumer is only going to install it once if they are ever going to install it. And maintaining it, there's no hope of maintaining it. Right? So you've got to build it in such a way that it is going to last for a long time. So those are some of the things we're working on. You can also imagine deploying this for general purpose smart home sensing. You can do health monitoring of the individual. You can wear these sensors in particular. So one thing I do is I wear this sensor node where it has a little accelerometer on it that you can just wear, and throughout the day it's actually just tracking my movement patterns, and then basically it's a digital pedometer. When I come home, it can just suck all the data off. And because it's so low power on the wireless side, you don't have to worry about recharging this thing over and over again. So there's a lot of new uses that we can think of for why you would use long-lived wireless sensors. And finally, the last thing is, because it's so low power, some of the work in wireless power or batteryless technology actually becomes feasible now. At 65 microwatts, you can start to do wireless power transfer techniques. You can easily run this off of a solar cell. So you can start to imagine some of these power harvesting techniques powering this thing. So one of the things that we found is one of my colleagues at UW, Josh Smith, who's been doing long-range power harvesting off of HDTV signals. You can actually power the Snoopy node using the signal emanated from an HDTV signal source. So you can just have a little antenna on it that's basically harvesting the energy from the HDTV source, because that's usually 100,000 kilowatt output. And if you're in a reasonable range of it, you can use that energy. So you don't even need a battery in that case. So in summary, I talked about two different sensing approaches that my lab has been working on. First is a single point sensing solution for energy and water sensing, basically figuring out ways that we can disaggregate consumption in the home down to each appliance and fixture. And the second piece of technology that we've been working on is using this power line coupling approach to build ultra-low power wireless sensors for general purpose wireless sensing applications in the home environment. One of the things that our lab has been doing quite a lot of recently is looking at ways that we can show impact outside the academic space. And so some of the work in energy monitoring that we've been doing was we formed a company a couple of years ago, and earlier last year was acquired by Belkin. So Belkin is a large consumer electronics company. They do wireless networking, they do iPhone, iPod accessories. So they actually purchased our startup company before we even got funded, before we did our VC round, a round of VC funding, and they're actually commercializing and building some of these energy monitoring technology. So both for a consumer electronic device and as a utility device that utilities will be deploying. And so this is just a sneak preview of what that device looks like. So this is a little plug-in module, kind of looks like a router. It plugs into the power line. It does all the DSP signal processing. And then could be an in-home display that gives you some feedback. Or you can go to a website to get that same information. So this is something that we're really excited about because of all this work is starting to actually see the day of light really soon. So with that, I'll take questions. And I want to thank some of my grad students that have been working on some of the energy monitoring and the low power sensing work as well. So thank you. Yeah.
Back to consumers for
Yep.
electricity. But the big question becomes, there's a lot of pushback, people saying, oh, you're data mining me and you're going to use this information for other things.
Right.
How do you address the privacy concerns?
So one of the things I didn't talk about is you can take all of this research and turn it on its head and start a whole other research agenda, which is the privacy implications of in-home sensor monitoring, right? If you look at that chart I showed you, with that one plug-in module, I can figure out exactly what people are doing in their house, right? And that's actually kind of scary, right? So one of the things we've been doing is looking at a couple things. One way is how do you secure the data in such a way that you can convince the consumer that this data is actually going to be private? The other thing is, can we obfuscate the data in such a way that the homeowners are the only ones that need to look at that data, right? We're changing their behavior. So can we present the data in such a way that they get this great breakdown of consumption, but the data that the utilities and the federal government might be looking at for data mining applications is actually just in the noise. In fact, what they're looking at is an aggregate view. You know, this area in Washington has this kind of profile, rather than saying this person has this profile. So one thing we've been doing there is looking at data obfuscation techniques where when it comes out of the DSP sensor, when it goes back to the cloud or somewhere else in a database, it actually sends this aggregate information. The breakdown information can stay local to the home itself. So only if you're in your physical home can you see the breakdown. Outside of the home, you can't see it. So that's one way to mask that. The other things we've been doing is looking at ways that you can educate the consumer. You know, there's a lot of interesting analogies here where, you know, look at your credit card bill, right? Credit card transactions. There's a lot of personal information that's mined by the banks in that case, right? And there's a trade-off between the personal motivation and value add versus what you're giving up, right? Every Google query you make is a huge amount of data that's being sent over the wire, right? And so I think the mental model has actually been swayed in such a way that, oh, you're monitoring me, and as a result of monitoring me, you're going to get all this information. But if you educate the consumer about what can you really get from this data, I think they'll start to learn, right? I think part of it is because sensing in general is already scary. And I think what we've been doing is looking at ways that you can, when you install this technology in a consumer's home, is educate them about what exactly is happening. I think they'll start to understand that, all right, there are some implications, but the likelihood that somebody could data mine this and do these inferences is really far-fetched. They're more likely to do some data mining on your credit card bill, right? Yeah, you had a question?
On your sensor network, your nodes,
Uh-huh.
the power line antenna stuff,
Yeah.
what lines are you actually using? Are you just using the ground wire, for example? Or?
So it depends. So if in a properly wired home, we use a ground wire. In some homes that are older that don't have a ground return, we use the neutral. Yep.
And how far does that propagate that through?
That's a very good question. So the largest home we tried this in was a 10,000 square foot home. It was 4 stories. We did end to end. It's hard to figure out the actual length of Romex that's in the wall, but we tried to estimate it as best we could. You know, here's the breaker panel. Here's a home run wire. We were actually getting great signal in a 10,000 square foot large building. So right now we're trying to characterize that. It's not easy to characterize just because even if you have a large space and you have maybe 100,000 foot of Romex, you'll still get good coupling because of some other reasons. For example, you might have a loop that's coming around, or you might actually get coupling through another wire. So it's hard to control it, right? But I think the rule of thumb is that in a general home environment, single family dwelling, you'll definitely get full range. In a building like this, I'd say you won't get, there's no way you'll get coverage in a whole building like this just because of the impedance of the power line, right? Signal's not going to propagate. We're trying to characterize that now, but we don't have a good answer to that because the phenomenon is so hard to grapple.
Does this, for example, would your neighbor be able to pick up stuff?
So that's a great point. So in the neighbor, if you have a single family home separated, your neighbor won't pick it up because what will happen is the signal goes to the breaker panel, the impedance from the breaker panel to the pole top, You're going to get a lot of loss there, and then you're going to get a lot of loss in the transformer can, right? So you're not going to get it back to the power line. Your transformer can and your little short leg is enough of a buffer to prevent these signals from leaking over, right? Even if they did, it's almost like Wi-Fi leaking over into your neighbor, right? But where you do see it is in, let's say you install it in a condo or an apartment. You might see it in a shared wall, right? You'll obviously see it because the power lines are probably shared between a single wall, right? Then you might see some leakage there. But yeah, it's the same analogy as there as Wi-Fi, right? It's like picking up signals over the air. Instead, you're just plugged into an outlet. Yep. Yeah.
When you're detecting switching power supplies, does it matter if the power supply uses power factor correction or not?
Oh, that's a very good question. So it does. So most of the consumer electronic standard grade ones, they usually don't use really advanced power factor correction. Some of the more high-end industrial grade kind of appliances do, and so we just started looking into that. What we do is we try to model the power correction factor as a separate entity. So we say, can we identify this as a TV, and do we see some supporting circuitry that's doing some power factor correction? If it is, then we use some kind of a probabilistic model for that one, right? Because the problem with the power correction factor is it makes the power supply look really different time to time, right? One time it might look like a TV, the other time it might actually look like a PC, for example, right? Because it's so dynamic. So in that case, we try to tease it apart. But in general, for most of the consumer grade appliances and devices, most of them don't use any of the PF circuitry. But yeah, it does make it pretty challenging.
So on your power sensing,
Yep.
how accurate are you on non-switch loads,
yeah.
loads, like pure resistive loads, for
Yes.
example?
Yeah, so pure resistive load, what we do is we use 3 different features for that. One is we use the power change. We use the voltage and current phase angles. So in that case, it better be 0, right, if it's purely resistive. Often, a lot of purely resistive loads aren't purely resistive unless it's an incandescent light bulb or a halogen or something. But if there's something that's a combination, we use the other thing. Let's say you have a hairdryer, right? You have a resistive component that comes on with an inductive load. So we piece it together. So we use some inductive component there. But for an incandescent, it's hard for us to tease apart which one's which. But we know it's an incandescent light bulb based on just the fact that it's a purely resistive load and that we see a transient switching phenomena that happens from the light switch. So what happens is when you flip the light switch, you don't get a continuous noise source. You get a transient that happens at the 60 hertz. So we use the transient plus the power current relationship to figure out if it's an incandescent. So incandescents are some of the hardest to detect, even though they're the simplest in terms of the construction of them.
Okay, and then on your water system,
Mm-hmm.
does it matter if you put the pressure sensor near a user? Like if you, for example, instead of putting it on the hose bib,
Yep.
if you tapped in at your washing machine.
Oh yeah, that's a good question. Let me bring up the diagram of that. That's actually an excellent point. The reason why, so yes, yeah, you can. Let's say you're not in a home, you don't have a hose bib. Let's say you're in an apartment or in a condo. So one place you could put it is on the water heater. So most water heaters, actually all water heaters have a drain. You're technically supposed to drain your water heater every year. Most people don't do that, but you're supposed to drain it. And so there's a drain here that you can screw it onto. So we've tried it there and it works fine. The other place you can put it on is, you can put it on behind your dishwasher or washing machine. It's probably easier to access. Or you can put it down below a sink, just one, right? You can put it in line with a sink. In fact, that's what we do for the condo and the apartment deployments is they don't have water heaters or a spigot, so we just put one under a sink, and it still gives them, it still works fine. Yeah. Yep. Yeah, it can go in line here, but you don't have to put one everywhere, right? Yeah. Inline is a little bit harder because you got to turn off the valve and unscrew it, but it's still doable then compared to cutting into this thing here.
Well, as long as it fits on whatever.
Yeah, it's a 3/4 inch compression standard, so that's why we try to use the spigots more often, just because that's easier. But that's a possibility. So the other thing that we had one homeowner do was they had a utility sink that they didn't use quite often. What they did was they screwed it onto the end of the utility sink where the faucet was coming out, and it has a little threaded connector there for putting an aerator on. So they unscrewed the aerator, screwed the hose sensor on there, and just kept the water on. And they never used the utility sink, so they used that as their sensing point. That was really easy for them to do. So, another thing to point out is you have these in your homes, which are called thermal expansion tanks. So when the hot water gets really hot and you have back pressure, this is to prevent things from pressure from expanding in your plumbing and causing damage to your fixtures. And so this actually acts as a pressure dampener. They even sell water arresters, pressure dampeners, where if you quickly close a water valve, the back pressure can actually damage one of your fixtures. So new homes have water pressure arresters. Even with those, we can still easily see the signal because what they're trying to dampen are the huge transients, the 50, 60 psi transients that occur over the baseline pressure. What we're detecting are the small, sub 1 psi water fluctuations. So even having dampeners in there, we can still see it.
What was your accuracy on water flow detection?
Oh, yeah, so I didn't talk a lot about that. Yes, so water flow detection, so that's a really interesting space just because getting ground truth is hard. Water meters are actually about 10 to 20% off, right? So as they get older, they get more and more inaccurate. So what you could do is you can actually, if you think your water meter is too inaccurate, you can call your local municipality and say, I want to recalibrate my meter. And what they tell you to do is, they tell you to get a calibrated 1-gallon bucket, you fill it up, count how long it takes, try again, do it 5 times, and you average it, and you give them that number. That's how they calibrate their meter, all right? So it's hard to get ground truth, but we tried our best, right? So what we did was we used the calibrated bucket technique, because that is actually more accurate than a meter. And so we were able to get within 0.1 GPM, 1.1 gallons per minute, which is about 2 to 3% error from bucket trials, which is actually pretty interesting because that implies that technically the water pressure method of inferring consumption is more accurate than your water meter that's outside your house. So the way we're doing it is because, so pressure is not directly related to flow, right? It's pressure plus resistance is equal to flow. So what we're doing is we're modeling the resistance in the home to infer what it is. So it's not a direct calculation. There's a statistical model underlying it. But that's one thing that's interesting. But the other thing that's kind of fascinating is turbine-based water meters. So how does a water meter work? Water goes through a pipe. There's a turbine in there that spins, and it spins a dial, it spins a magnet, and the magnet in turn spins the clockwork. All right? So it just spins in one direction. But turbine-based water meters are only precise down to 0.5 GPM. If you only consumed water less than 0.5 GPM, you can actually consume water without the meter ever moving. You can steal water in a way by moving water at such a low rate, and you bank it up, and your thing would never turn. So in this case, because this goes down to 0.1 GPM, you can actually get that small fluctuations and small consumption. Because now we're getting to a point where you have low-flow shower heads, low-flow shower fixtures, and low-flow toilets where they're less than 0.5 GPM. And you're not going to, and so traditional water meters won't even be able to detect that if you're just using it in isolation. And so the pressure-based approach gives you the smaller changes. So.
Does it also get bothered by neighbors or other people on the water main?
Yeah, that's a good question. So more so in this scenario than electricity, right? Here, it depends. If you have a pressure regulator, which most new homes do, so the idea here is if you have a huge spike, let's say something happens, let's say a backhoe hits a pipe, you don't get that transient pulse going into your home because that's going to damage everything. So if you have a pressure regulator, it doesn't happen, right? Here you get clean pressure coming in, you get nothing coming out or coming in, right? So in these scenarios, it doesn't matter, right? The water meter itself actually gives you a little bit of a buffer as well. So because it's a spinning turbine-based solution, it actually buffers it pretty well. So where you do see a lot of overlap is in places where it's not individually metered. In an apartment, if there's only one meter for the apartment, you'll see everybody flushing their toilet, right? You'll see all the things happening in the whole apartment. Every now and then, you'll see some large changes. Like let's say if you live near a fire station or a fire department, what they do is every night they test their fire hydrants, right? They'll actually full force turn them on. What will happen is your general water pressure will drop for a few hours and come back up. So that's just the whole infrastructure changing, but it doesn't change the waveform itself. Yeah?
Is it possible to tell from the water data when
Yep.
the hot water heater comes on?
Yeah, definitely. So I didn't go into detail about that, but when I talked about how hot and water are technically connected, so here we're monitoring not just cold water use and event detection, but hot water detection as well. Because if you know roughly the size of your water heater, you can model the water heater dampening effect. Like I said, this is a capacitor, right? So when it goes through here, you can detect that, oh, hot water was consumed. So the reason why that's important is a significant portion of your energy bill, if it's electric water heater, is electric water heating, right? So that's why it's important. The water flow sensing also disaggregates between hot and cold water use. So here's how much water you consume that's hot, and here's how much water you consume that's cold. That's also really important. And the municipalities are really interested in doing that, but right now there's no easy way of doing that unless you cut into these two pipes. Yeah, you had a question?
Well, are there any techniques out there which are applied to detect change in water flow or pressure?
So most of it, there are some simple techniques that are typical. What's that?
Are they applied?
Yeah, so in this space, there hasn't been a lot. In general, there's very little work in water sensing altogether, right? Some of the most work I know, some of the techniques are for long haul water pipes, not at the end use homeowner side, but on the huge, 12-inch pipe that's feeding a main street. They've used acoustic and ultrasonic kind of sensing to look at these waveform propagations to see if there's a leak or an infiltration or a cut or something. So the signal processing community has looked at that for a while now. But it's mainly looking at time of flight and kind of that kind of analysis to figure out if there's waves are propagating. Yeah, we don't use time of flight here, but we could. You could imagine putting a sensor here and looking at the time of flight of the waveforms and doing a superposition of them and seeing how they're shifted. But we've done that, but you don't need to, because in a home you only have maybe 20 fixtures at most. So when you do it in a large building like this, you'll get more benefit from it. You had a question?
I seem to draw an analogy between electricity and sound,
Yeah.
and water and
Yeah.
air pressure.
Yeah.
How much have you considered that? And how much can you detect a door opening?
Oh, yeah.
That's
That's interesting to bring it up. Let's see if I have that. I don't think I have the main side, but I'll bring this one up. So the general work of infrastructure sensing is using the utility as a sensor. So one of the things I show here is air ducts. So a couple years ago, in 2008, we built a system which was a sensor that goes onto your HVAC, your central home air conditioning and heating systems filter. It goes on the filter and you slide it into your HVAC unit. What it does is it actually monitors the change in the pressure differential in the HVAC unit to infer where people might be walking in the home. So as people are walking, opening and closing doors, you see changes in the air pressure. So you have the return duct, supply duct, and the change in air pressure manifests itself in the air plenum of the air conditioner. So at one sensing point in the AC, you can actually start to do door detection and even roughly use it as a motion detector of people. So that can be used for smart heating and cooling applications where the air conditioner not only is modulating where it needs to modulate the temperature, but it also does the sensing on figuring out where people might be residing. So we've done a little bit of that. Yep. Acoustic propagation we haven't done too much in. There's others that in the research community that have been looking at that where you kind of do energy monitoring acoustically, listening to the microwave beep, the door fridge open and close, listening to the stove click on, using those kind of secondary acoustic features to potentially figure out what appliances just turned on or off is something that I've seen others work on. Let's go here.
Earlier in the energy and frequency monitoring, you mentioned that you can detect most equipments. What sorts of equipments can you detect?
Yeah, so some of the things that are hard to detect might be resistive or incandescent lights. Let's say they overlap with another event. Let's say you turn your TV on at the exact same time the TV turned on, the light bulb also turned on. So what will happen is the TV will mask the event of the light bulb, for example. So very resistive loads, purely resistive loads, are easy to miss, just because you don't really see any other secondary effect. And if you look at the power data, you have something else that's superimposed on top of it, so you can't really tease it apart. So resistive loads are pretty challenging. If they're offset by a few hundred milliseconds, then we can pick them up. But if they're simultaneous, it's hard to pick up. Some really small loads are hard to pick up. So the charger for the iPhone, the little tiny charger, is actually really noisy. So we can pretty much pick that up most of the time. But if it's really far away in the home, the signal might attenuate to, let's say the sensor happens to be in a bad spot, it might attenuate so that you don't even see it. So really small devices that are sub maybe 10, 15 watts might be undetectable just because they're not very noisy or they're not very loud. But a lot of it ends up being either masked events of resistive loads or loads that are just not very powerful. Yeah.
For the energy and the water monitoring, if the residents install a new device, how do you detect such kind of
Yeah, that's a good question. So, one of the things we do is when you install a device, we kind of get this model of what's happening, right? It takes a day or two. If they train individually, then it's fine, right? The day of, you have a trained model. But over time, you're going to have, everybody doesn't use everything in one day, right? It takes a couple of days. So what will happen is when that thing first comes in, if it's something brand new, let's say it's the new Xbox 4, right? And nobody's ever used it, and you're the first one to bring it in, it'll say unknown device. It'll try to categorize it. It might say, that looks like a gaming station, or it might say it's a PC or something like that, but it's not going to know until you train it or our model in our cloud has actually labeled it already. So it'll say unknown, but it'll try to guess the category. So it'll guess what kind of category it is, but eventually, if it gets an example from either the person in the home of training it, or we have an example in the database, then it'll get populated. Yep. Do you have a question?
So you're relying on people continually kind of tagging their own devices?
No, so yeah, that's one part of it. One way is, so the motivated homeowner who really wants to be eco-friendly, green technology, will calibrate it, well, they'll do it, right? So we'll take advantage of that opportunity by putting that data in the cloud, right? But the second portion of it is we're mining it off the FCC data sheet, so we already get the data. They're in a way just confirming our models, right? Even if they didn't train it, they're just confirming it. So we get this check mark in the database, right? And the third way is we have these generic models that we're creating for these different appliances that even though we might not know it's an Xbox, we'll know that it's probably a gaming platform or a computing-like device. So there's multiple ways to get that information. I think crowdsourcing is just one piece. It's not the only way of doing it. Did you have a question?
Yeah, on the, another question on the electrical monitoring system. How important is it to, like what phase you're getting it on? I mean,
Yeah.
do you have to plug in on low phases?
So that's a very good question. So homes in the U.S. are split single phase, right? So you get 122 legs, combined you get 240, right? So what we're doing is we're actually monitoring on one leg. You could install one on each leg, but the problem is finding the two legs from a homeowner's perspective is really hard, right? I guess you could have a light that lights up and you try all these outlets. If it doesn't light up, it's a different phase, right? But what we do is we only put it on one and assume that the bus bar and the power line, the power lines in the bus bar and the breaker panel, they're close together enough that they inductively couple over, and they do. Let's say you have an incandescent light bulb on phase 1 and your sensor's on L2, you still see it on L1. L1's data on L2 because they're coupling across the bus bar. And they couple across a very wide frequency band, maybe tens of hertz to up to megahertz. They couple it right across that band. That's how PLC works. So power line communication is the notion of using the power lines for Ethernet. So you can run Ethernet over your power line, for example. So if you ever look at their thing, you actually don't need a repeater, because what they assume is they assume some leakage across the two. But for effective, if you want really good throughput, you actually install a repeater. X10 even offers something that repeats the signal.
Yeah, Insteon, we played with that for a while.
Yeah, Insteon. Oh yeah, yeah. So because we're not looking at data transmission, it doesn't matter. We still see the waveform and the signature. For Snoopy, it doesn't matter either because Snoopy, all the grounds are tied together, and neutrals tied together.
So just out of curiosity, the actual for the electrical system, the actual sensing, is that a very expensive piece of equipment, or?
For the power line and back protection.
Yeah.
No, it's designed to be. It's an embedded microcontroller computer with a DSP in it, and with an Ethernet or Wi-Fi chip. So it's designed to be fairly cheap, low cost because it does some of the signal conditioning and feature extraction, and all the more advanced things happen in the cloud.
So the real hardware is probably $30 to $50.
Yeah, I mean, think about a router. How much does a router cost, right? Like to manufacture costs less than $10.
So is that going to be a problem or using that kind of system for power event detection in like an apartment complex?
Yeah, it depends. If you're in a newer apartment complex where a lot of those are mandated to have individual meters, and some of them do, then it's not an issue, right? Because your meter is downstairs somewhere, you have your own thing. It's actually, in fact, better for apartment dwellers because you can't even look at your meter, right? It's somewhere in a cage downstairs or somewhere, right? So, in that scenario, it's fine. But in retrofits, well, you see a lot of this in Seattle where it used to be maybe a hotel or whatever, and they're converting it into a condo, and they only have one meter. Then it's a little bit of a challenge because you have so many events going on. And we're just now looking into that space where, if you have a huge space, can you tease apart these signals? In that case, you have so many events going on that it's a harder signal processing problem.
Fuse boxes.
Mm-hmm. Fuse boxes, I just completely ignore. I see a fuse box that's like, you got to get rid of this thing.
Oh, you don't have that choice. Okay.
Yeah. We haven't touched fuse boxes yet.
We try not to, but they show up.
Yeah. So you could depending on the kind of the fuses. I mean, at least breaker panels have a de facto standard, but fuse boxes are just all over the place. But certain kinds of fuse boxes, our contactless current sensor works on some of them, not all of them. The ones that still have bus bars, it'll work with, but a lot of them don't. A lot of them are actually inside of it. If you look inside the fuse box itself, underneath it, it's just a bunch of jumper wires, right? But the ones that have a bus bar with screw-down terminals on top, I think it will work. But yeah, those are just, yeah. They're not allowed anymore, so that's the issue. So when you sell your home, you got to update a fuse boxed home. So we're hoping that eventually they'll get phased out.
Yeah. Okay.
Yeah, that's a hard one, very hard one.
Apartments with fuse boxes.
Oh, yeah, that's like compounding on top of it. Yeah. So actual apartments that are rented out that have fuse boxes in them. Okay, that's interesting. Yeah, yeah. I mean, yeah. Technically, those are all supposed to be phased out, right? Because
It will be once the residents move out.
yes. Okay. Yeah. So if folks have been in there for the last 10, 20 years, then.
Yes, they have. It's an elder care facility.
Oh, okay. Yeah. Yeah. You won't see that anytime soon. So I guess one thing you could do is you can still use the power line monitoring technology.
Well, that's
And you can infer the consumption by saying, okay, if I see a TV that's roughly this much power, or if you're only interested in event detection, then you don't need power data at all. Then you only use power line event detection. So the event detection will work in fuse boxes. But when it comes to like power monitoring, it's harder.
the event detection is a little more.
Yeah, the event detection would yeah, that's fine. In fact, we actually did a fuse box home with that.
Okay.
Uh,
That's good.
Can we just do like our own CTs or something like that?
yeah, exactly. If you can get in there and just do that. Yeah, with the CT data, with the current power and the voltage, you got everything there. In fact, the fuse boxes are easy to do CTs with.
Yeah.
You know. It's actually exposed. It's exposed, yeah.
So of course, the ones we're seeing are this big.
Okay.
Little tiny.
Huh.
Oh.
Interesting.
What about putting your contactless sensor right on top of the main fuse?
Yeah, on a breaker or a fuse, we tried doing that. The problem we did, so in the breaker example, we don't do that because the NEMA, the national, so the NEC and NEMA code requires that you can't put anything on the breaker, because what will happen is if you put it on the breaker and it happens to shift, and the breaker tries to flip, you might get it jammed, right? So you're not allowed to put anything on the breaker. On the fuse you could, but I haven't tried it yet.
Here, have a look.
Yeah, I've seen those.
Yeah. It's just,
Yeah.
well,
Four fuses basically powering that whole area.
yeah. Well, this was about a 400 square foot apartment.
Yeah, well, still 4 fuses. In a 400 square foot modern apartment, you have at least 8 or 10 breakers.
Yeah.
So. Cool. Great, thank you.